Good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be solving the October-November 2023 Physics 0625 Paper 2, Variant 2 of the Cambridge Assessment International Examination. Without delay, let's go. Question number 1. Which quantity is a scalar quantity? A. Acceleration. B. Force. C. Time. D. Velocity. All other questions but time are vector quantities, okay? Only time is a scalar quantity because you can't tell us the direction of time, okay? But you can tell us the direction in which a force goes. So you can tell us the direction of acceleration and you can give the direction of velocity. So time is the only scalar quantity. The correct answer to question number 1 is C. We go straight to question number 2. A student measures the average speed of a cyclist in a race. Which quantities must she measure? Okay, to measure average speed, average speed is total distance divided by total time taken. Okay, average speed, average velocity is total distance covered divided by total time taken. So, total time taken to complete the race and the time taken for the cyclist to reach a higher speed. No, total time taken to complete the race and the total distance traveled by the cyclist at a higher speed. No, not higher speed. Total time taken to complete the race and the total distance traveled by the cyclist. Yes, total distance and total cycling. Total distance and total time taken for the cyclist throughout the journey. Okay, yeah, we don't need option D. The diagram shows a series of images of a moving object taken at regular intervals. The object is moving from left to right. So you have the object moving from left to right. Which statement describes the motion of the object? Take note of the spacing between the dots. The spacing looks equal, okay, from here to here. 1, 2, 3, 4, 5, 6. From dot number 1 to dot number 6, the spacing looks equal. And then the spacing began to increase. What can you conclude from here? You can conclude that this is a case of an object moving at a uniform speed, okay, uniform speed, then the object then began to accelerate at that dot 6. So uniform speed, then began to accelerate, and that is what we have here, okay? Yeah, if you were to plot the graph of if I were to plot the velocity time graph, time, velocity, this is what the graph would look like. We have uniform speed from beginning up to point 6, then the object began to accelerate. So let's see. The object accelerates continuously, no? The object decelerates continuously, no? The object travels at constant speed and then accelerates. Correct. C is the correct answer to question number 3. We go straight to question number 4. A plastic ball has a mass of 4 grams and a volume of 20 cm cube. There is a crack in the ball's surface. The ball is placed in water. The ball is placed in a bath of water. Water leaks into the ball without changing its volume. Yeah, without changing the volume of the ball. And eventually the ball sinks. The density of water is 1 gram per cm cube. Let's take note of that. Which mass of water has entered the ball when the top of the ball is first level with the water surface? When the top of the ball is first level with the water surface. All right, let's look at that. This is the mass of the ball, this is the volume of the ball. If you calculate the density of the ball, divide the mass by the volume, you get 0.2 gram per cm cube. That means ideally the ball is supposed to float in water, okay? If this was the ball will be expected to float in water. The ball has a crack. But now, because of the crack, okay, water began to enter into the ball. Yeah, so water enters into the ball until it eventually looks like this, okay? The ball is exactly at the same level with water surface. So at this stage, we can say the density of the ball must equal to the density of water. I mean the density of the ball that is filled with water. Here the ball is filled with water. The density of the ball filled with water must be equal to the density of water. That's why it stays at the same level with water surface. If the density of the ball is higher than density of water, the ball sinks, goes down to the bottom of the pool. And if the density of the ball were lower than density of water, then the ball continues to float, just as it was in the first case. Okay. So for the density of the ball to be equal to density of water, it simply means density of the ball when filled with water must be equal to this density of water, 1 gram per cm cube. How do you calculate the density of water? Of course, you already have the density of water, okay? So for this ball to be at the same level with water surface, the density of the ball when filled with water, density of the ball when filled with water, okay, that's density of ball filled with water, must be equal to the density of only water, okay, which is 1 gram per cm cube. How do we get density of ball and water? That will be mass of ball when filled with water, mass of this ball when filled with water, divided by the volume of the ball. Take note that the volume of the ball remains 20 cm cube. The ball does not expand, okay? And this 4 gram is the mass of the ball without water. So this is not what we are using. We are using the mass of the ball when filled with water. So density of the ball when filled with water equals to mass of ball when filled with water divided by the volume of the ball. And it must be equal to density of water, which is 1 gram per cm cube. Now let's solve this question. Density of ball plus water is mass of ball plus water divided by volume of the ball. Volume of the ball is 20, and this must be equal to, density of ball and water is equals to, okay, let me not go this way. Let me take it easily. Density of ball when filled with water equals to mass of ball when filled with water divided by volume of the ball that is filled with water. Okay, and volume of the ball when filled with water is the same thing as the volume of the ball, which is 20 cm cube. Yeah. So, and if you get this, if you calculate this, you must get the same value with the density of water. And density of water is 1 gram per cm cube. You know, that's the only condition for the ball to remain at the same level with water surface. Yeah. So you are supposed to get 1 gram per cm cube. Okay, so now let's substitute mass of ball when filled with water. We do not know mass of ball when filled with water. Volume of the ball is 20. Okay, so you divide by 20. If you calculate this, you should get density of water, which is 1. So from here, if we cross multiply, you get mass of the ball when filled with water should be equal to 20 multiplied by 1 should be equal to 20 gram. Okay, yeah. So mass of the ball that is filled with water is 20 gram. But we have the mass of the ball only as 4 gram. So what will be the mass of the water that we poured inside, that entered into this ball? Mass of the ball only is equal to mass of the ball when filled with water minus mass of mass of the water that entered the ball. Mass of the water that entered the ball equals to mass of the ball when filled with water minus mass of the ball without water. Okay, yeah. Mass of the ball when filled with water is 20 grams. 20 minus mass of the ball only without water being in it is 4. So 20 minus 4, we get 16 grams. That's the mass of the water that entered the ball, okay? So that's how you get the mass of the water that entered the ball only, okay? If this is not clear, please, you may watch how I solve this number 4 again to make it clear to you. Yeah, get used to watching the video of a question over and over again till you understand it and then you proceed. A satellite orbits the Earth at a constant speed in a circular orbit. Which statement is correct? A circular orbits the Earth. This is the Earth, a satellite. This is a satellite. If a satellite is orbiting the Earth, there is a centripetal force on this satellite which acts towards the center of the Earth. Okay. The resultant force on the satellite is 0. No, there must be a centripetal force. Forget the fact that it's at constant speed. The fact that something is moving in a circular orbit along a circular path, there will always be a force called centripetal force acting on it. And the direction of the force is towards the center of the circular orbit or the circular path. So the resultant force on the satellite is 0. That's wrong. The resultant force on the satellite is towards the Earth. That's correct. The resultant force on the satellite is towards the Earth. That's correct. Resultant force of the satellite is away from the Earth. That's wrong. Resultant force of the satellite is the direction of its motion. No, it's just towards the center of the Earth. The correct answer to number 5 is B. We go straight to question number 6. The diagrams show 4 identical objects. Each object is acted on only by only the forces shown. What are those forces? Which diagram shows an object in equilibrium? Okay, so we have two forces of 10 Newton each, and we have a force of 20 Newton downward. Total forces to the upward equals total forces downward, right? Good. What about moment? Okay, there will be a resultant moment. These two forces are coplanar. Okay, why this one is um is not coplanar with this one down here. That simply means this force here will try to produce a resultant clockwise moment and try to make the object rotate in a clockwise direction. Hence, this one is not in equilibrium. Here, forces upward 10 plus 10, 20. Total forces downward 10 is not definitely not in equilibrium. Forces to the left equals force to the right, 10 equals to 10, yes. Force upward 10, force downward 0. This one is not in equilibrium because force upward must equal to forces downward. Forces downward 10 plus 10, 20. Forces upward 20, balance, right? Yeah. What about moment? Well, the resultant of these two 10 forces will be a single force of 20 Newton, okay? The resultant of these two forces will be a force that acts in between them and of the magnitude of sum of each of these, which is 20. And that is coplanar with this 20 Newton force. So that means D is the only one that is in equilibrium. That makes B the correct answer to question number 6. We go straight to question number 7. A resultant force F accelerates a car of mass m along a straight horizontal road from rest to a speed v in time t, giving its momentum p. Which pair of relationship for this situation is correct? P times t equals to mv. Impulse equals to change in, sorry, impulse, symbol for impulse is I. Impulse equals to change in momentum, okay? And formula for impulse is 4 times time. Change in momentum is mass times v minus u. Since initial velocity is 0, since u is 0, from where? Since u is 0, okay, ideally the formula is v minus u. Since u is 0, then it's not necessary to put it in the equation, okay? Yeah, so Ft equals to mv. So do you have this formula here? Pt equals mv, F equals to impulse times time, impulse equals to mass times velocity, yes. Force equals to impulse times time. Yes, yes, B is correct. Why? Because, impulse equals to mv, impulse equals to force times time, and impulse is equal to momentum, which is mv. Okay, so you can say impulse equals to mv. We can also say the momentum equals to mv. Okay, yeah, and yes, since momentum equals to F times time, momentum is equal to impulse. Yes, and yes, that's it. Momentum is equals to impulse. So momentum equals to mv, and momentum is also equals to force times time, because force times time is impulse. Force times time is impulse, and since impulse equals to the change in momentum, okay, since initial velocity is 0, then you don't need to talk about change in momentum. Just focus only on momentum, okay? Okay, because the momentum is changing from 0 to maximum value. So just focus on momentum. Impulse equals momentum. So where do you have this formula? Impulse equals to mass and velocity, sorry, momentum equals to mass and velocity, impulse is also equals to, sorry, force equals to impulse times time, force equals to momentum times time, impulse equals to mass and velocity, correct. Force equals to impulse times time. How do you get that? Because force equals to change in momentum divided by time. This can be correct. Force times time is equals to impulse. Yeah, if you cross multiply here, we get impulse force equals to force times time. So this is correct. Also, momentum equals to mv. Oh, C is the correct answer. Yeah, that's where you have correct formulas. The diagram shows part of a roller coaster. This is the roller coaster. A roller coaster ride with the car at different positions. The car here, 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 and here. The car runs freely down from position X to position Y and up the hill to the other side. What happens to the energy in the kinetic store and the gravitational potential store of the car as it moves from position X to Y? Here, from X to Y, potential energy is reducing, right? Good. And what happens to kinetic energy? Kinetic energy will be increasing because it accelerates downwards. Potential energy reduces, kinetic energy increases. Kinetic energy increases, yes. Gravitational potential energy decreases. That makes option C the correct answer to question number 8. Question number 9. A box initially at rest at the top of a rough slope. The box slides down the slope. The box slides down the slope. The slope is 4 meters long and 2 meters high. The box does 10 joules of work against friction as it slides down the slope. Okay, what is the speed of the box as it reaches the bottom of the slope? Well, at the top, the box has gravitational potential energy. Yeah, while at the bottom down there, at the top, it has gravitational potential energy. While at the bottom down there, it has kinetic energy. Okay, but while sliding down this slope, it will be doing work against friction. Okay, yeah. If this is the box, there will be friction between the box and the slope, and that friction consumes energy. Okay, and the question has told us that the friction consumes 10 joules of energy. Now take note that the kinetic energy at the bottom of the slope equals to gravitational potential energy at the top, okay, at the top here, gravitational potential energy at the top here, minus work done in friction, okay, minus work done against friction. Yeah. So how do you get the kinetic energy? Yeah, we do not know, but we know kinetic energy, formula for kinetic energy is half mv squared equals to gravitational potential energy is mgh, where mass times gravity represent the weight of the box, and we already have the weight of the box as 20. So mass times gravity is already 20 Newton because mass times gravity is the weight, which is 20. So mgh, okay, that's gravitational potential energy is mgh minus work done against friction. Work done against friction is 10 joules. So this is what we saw to get the velocity. So let's see, half times mass times v squared equals to mg is 20, so I'm putting 20 here. Height, what's the height? Height is 2 meters minus 10 joules. Now take note of something. I said mg is the weight, which is 20 Newton. Since mass times gravity is equal to 20 Newton, and gravity itself is 9.81. So mass times 9.81 equals to 20. That simply means the mass equals to 20 divided by 9.81. How did I get 9.81? The question has already told us that I should take gravitational field as 9.8, not 9.81, 9.8. Yeah, we are using 9.8. Okay, that's what the new syllabus asks you to use. Okay, yeah, so IGCSE level use 9.8 as gravitational field strength on the surface of the Earth. Yeah, so I'm using 9.8 as the gravitational field strength. Let's go 20 divided by 9.8. We use our calculator. 20 divided by 9.8. That gives us 2.04. We work to two decimal places. 2.04, that's approximately 2. Yeah, we're working to two decimal places. Okay, so let's finish it up. The mass is 2 grams, right? Sorry, mass is 2 kilogram. Mass is 2 kilogram. So let's finish this up. Half times 2 V squared equals to 20 times 2 is 40. 40 minus 10 is 30. Half multiplied by 2 is 1. So we have 1 V squared is equal to 1 V squared is equals to 30. If 1 V squared equals to 30, how do you get V? V is equals to square root of 30. And if you take the square root of 30, you should be getting, you should get a value between 5 and 6. That should be 5.4, approximately 5.4. Use your calculator to do this, okay? You get 5.4 meters per second. That makes option A the correct answer to question number 9. Okay, well, I would have loved to take question number 10 before proceeding, but I have to tell you this, okay? I'll be having a free revision session with students that are taking the February-March exam and the May-June exam, okay? So kindly send me a message to my email, okay, so I can have your email address and add it to a Google Classroom, okay? So everything about the free online classes will be sent to your Google Classroom, to the Google Classroom. Okay, for free of all charges. But you must subscribe to my YouTube channel. Ensure you subscribe to my YouTube channel to be eligible to all of these. So just subscribe to my YouTube channel. This is my email, okay? Subscribe to my YouTube channel to have access to all of that. Okay, and I have so many videos that you can always have access to and watch at your own leisure time. All of these videos will help you to prepare for your exam. There are so many of them, okay? There's no crime in watching them all before your exam. Question number 10. An electric car is charged overnight. In 8 hours, 180 megajoule of energy is transferred. What is the power of the charger? Power is the time rate of dissipation of energy. Power is equal to energy divided by time. What is the energy in this case? Energy is 180 megajoule. 180 mega is million. 180 million joules. Convert 180 megajoules to joules, to kilojoules, okay? Because the power here is in kilowatts. So just convert to kilojoules. That means you divide it by 1,000. That will give you 180,000 joules. That's the energy. And the time is what? The time is 8 hours. 8. Time must be measured in seconds. Convert 8 hours to second. That means you multiply by 60 to convert to minutes. Then multiply by 60 again to convert to seconds. Okay. So you have 8 times 60 times 60. 60 times 60 is 3,600. So you just multiply 8 by 3,600. That gives you 28800. 28800. That's 28800. So what we are doing is just divide the energy by the time. Okay, the energy is 180,000. We divide it by 28800. It will be left with 1,800 divided by 288. 1,800 divided by 288. This gives us 6.25 kilowatts. Okay, 6.25 kilowatts. 6.25. To two decimal place, 6.3. That makes A the correct answer. Do not forget that because all the units of the reasonable units of the power here is in kilowatts. That's why I started by dividing energy by 1,000 to express it in kilojoules. This should be kilojoules. Yeah. So I have to express energy in kilojoules, okay, so that unit of kilo will appear in my work done, the power rather, which is watts. Okay, another thing you can do is the energy, just use it like that. Also, the time, use it like that. When you divide, at the end of the day, you'll be getting 6250, okay, watts. Okay, that's if you do not convert this to kilojoules. If you have used the energy like that, and if you have used the time in seconds, okay, energy in joules, time in seconds, you would have gotten 6,250 watts. This you can convert to kilowatts by dividing by 1,000, and that will give you 6.3 kilowatts, approximately 6.3 kilowatts. We go straight to question number 11. Question number 11, what does it say? It says, an object is a depth h below the surface of a liquid. The pressure due to the liquid at the depth is H, is P. Okay, yeah. The gravitational field strength is G. The density, what is the density, rho, of the liquid? What's the density? You know, the formula for density is the formula for pressure, okay, when we have density and gravity and height, is pressure equals to density times gravity times height, where the symbol rho represents density. How do you find the density? Divide both sides by GH. Divide both sides by GH. G will cancel out G, H will cancel out H. You will left with rho. Rho will now be equal to pressure over GH. That makes option D the correct answer. Okay, density is pressure divided by height times gravity. Option D is the correct answer to question 11. We go straight to question number 12. Brownian motion is the random motion of particles. In which state of matter is Brownian motion observed? Gases, liquids, solids. The particles of solids can only vibrate about their main position, okay? Solid particles only vibrate about their main position. They don't move about randomly. But in the case of Brownian motion is a random movement of particles. So particles of solids do not move randomly. They only vibrate about a main position. While the particles of liquid and gases move randomly. So it's only liquid and gases. Okay, gases and liquids only. That's the only case where you can observe Brownian motion. Question number 13. The volume of a fixed mass of a gas is varied. The temperature remains constant. Which graph shows how the pressure P of the gas varies with volume V? Okay, how do you get the relationship between pressure and volume? If we use this graph, it means pressure does not vary with volume. If you use this graph, it means as pressure increases, volume increases. And that simply means if we compress a liquid, so if you compress a gas such that we compress it completely, that the volume becomes zero, the pressure will be zero. That's what this one tells us. But it's not possible. Pressure of a gas can never be equal to zero. Okay? Pressure of a gas can never be equal to zero. Once you are compressing a gas for the volume to reduce, pressure increases. Yes. And if volume is increasing, pressure will be reducing. So this is not correct. This one shows that pressure does not vary with 1 over V. And this one shows that pressure varies with 1 over V. This shows that pressure is proportional to 1 over volume. This is the symbol of inverse proportionality. Okay, pressure is inversely proportional to volume. That simply means if you're increasing the pressure, the volume will be reducing. And if you're increasing the volume, pressure will be reducing. So this is the only relationship that shows us, this is the graph that shows the relationship between pressure and volume. Number 14. Liquid evaporates from a beaker. What happens to the temperature of the remaining liquid? And how does the temperature change affect the rate of evaporation? Temperature, rate of evaporation. And when temperature decreases, rate of evaporation decreases. Is that correct? When temperature decreases, rate of evaporation increases. That's wrong. If temperature is increasing, rate of evaporation will be increasing. And if temperature is decreasing, rate of evaporation will be decreasing. So, yeah, liquid evaporates from a beaker. What happens to the temperature of the remaining liquid? Good. Temperature of the remaining liquid now, not temperature of the liquid. Temperature of the remaining liquid. When liquid evaporates from a beaker, it is the highly energetic particles, particles that have high kinetic energy, okay, or higher temperature. You know, kinetic energy is related to the temperature. Yeah. So particles with high kinetic energy leave the liquid, while particles with less energy will be left. So the question is, what happens to the temperature of the remaining liquid? And how does this temperature change affect the rate of evaporation? Temperature of the temperature of the remaining liquid will be reduced, okay, and that will reduce the rate of evaporation. So temperature decreases and the rate of evaporation decreases, and that makes option A the correct answer to question number 14. No. Question number 15. Thermal energy, delta E, is supplied to an object of mass m, which does not change its state during the heating process. The temperature of the object rises by delta T. What is the specific heat capacity of the liquid? From our definition of specific capacity is the quantity of heat, okay, that's change in energy, required to raise the temperature of a unit mass of a substance by what? By 1 Kelvin. Temperature of unit mass, yeah. Quantity of heat required to change the temperature of unit mass of a substance. So this is what we should be having. Delta E over mass times change in temperature. A. That makes A the correct answer to question number 15. Question 16. A room is heated by a radiator. The diagrams X and Y show two possible circulations of hot water. Which heats the room? Sorry. A room is heated by a radiator. The diagrams X and Y show two possible circulations of hot air. Which heats the room? Which diagram and reason explain the heating by convection? Which diagram and reason explains the heating of the room by convection? Let's see the diagram X. Hot air rises, then cold air falls. Hot air rises, this is convection current. Diagram Y, when the room is heated, hot air moves this way. This definitely is wrong. So diagram X is correct, and the reason, air density decreases when air is heated. No, air density increases. Yes, yes, yes. Air density decreases when air is heated. Correct. When air is heated, it becomes lighter and it rises. Air becoming lighter simply means its density is reducing. So air density reduces when air is heated. That makes option A the correct answer to question number 16. You have to check the other option. There's no point. Question 17. A student writes down some facts. In your exam, it is advised you look through all the options, especially if you are not sure, okay? Unless you are very certain of your option, that's when you can pick an option and proceed. If you are not certain, please look through all the options and pick the most correct one. In fact, if you are not sure, then start kicking out the most incorrect answer, okay? The very wrong one, kick them out, strike them out, while the last one standing becomes your correct answer, okay? That's another technique you can use. Okay, and in multiple choice exam question, do not leave any question unanswered. Okay, if your time is almost up and you've not answered many questions, just make sure you pick. Don't leave any question unanswered. Okay, yeah. So if once you pick randomly, okay, like you have 1 minute left and you've not answered up to 10 questions, pick randomly. By probability you might get 2 questions correctly out of those 10. It's better than getting 0 from there. All right, we finish this up. The students write down some facts about two transverse waves. Wave 1 has a frequency f and velocity v. Wave 2 has 4 times the frequency of wave 1 and is traveling at a velocity of 2v. What is the wavelength of wave 2 in terms of v and f? Let's see. The students write down some facts about two transverse waves. Wave 1 has a frequency, so let me start with wave 1. Wave 1, V equals to F lambda. Let's go to wave 2. From wave 2 has 4 times the frequency. So V for wave 1 equals to F1 times lambda 1. For wave 2, frequency of wave 2 equals to 4 times the frequency of wave 1. Okay. Also, the wavelength of wave 2 equals to what? And it's traveling at velocity of 2v. Okay, not wavelength, it's velocity. The velocity of wave 2 equals to 2 times of velocity of wave 1. What is the wavelength of wave 2 in terms of F and V? What is V1 here? V1 is F1 lambda, right? Good, good. And V2, how do you get V2? V2 equals to F2 lambda 2 from speed equals to frequency times wavelength, right? Of course. Now, what we'll do is we are going to substitute the value of, for the value of V2 and for the value of F2. F2, okay, this is F2. Now let us substitute V2 equals to 2V1. So we have 2V1 equal to F2. F2 equals to 4F1. So we have 4F1 multiplied by lambda 2. Okay, lambda 2 is what we are looking for. The question says, what is the wavelength of wave 2? So you are looking for the wavelength of wave 2 in terms of F and V, where F and V are the frequencies and velocity of the wave 1. So if you want to find F2, you want to make F2 the subject, sorry, not wave 2, you want to make the lambda 2, okay, wavelength of wave 2. You want to make this the subject. So what we just do is, since, let me write this on the right, on the left hand side, since 4F1 lambda 2 is equals to 2V1. I just put this one on the right and then I put this one on the left. And that's what we have here. So to find lambda 2, we just divide both sides by 4F1. Divide this by 4F1. So what happens? You cancel out. F1 cancels F1. 4 cancel 4. So you'll be left with lambda 2. That's the wavelength of wave 2 equals to 2 here 1, 2 here is 2. So you'll be left with V1 over 2F1. Okay, that was 2V over F. Sorry, V over 2F. Okay, this one just means speed of wave 1 divided by frequency of wave 1. Okay, yeah, so wavelength of wave 2 is speed of wave 1 divided by 2 times frequency of wave 1, which is option D, V over 2F. Which makes option D the correct answer to question number 17. We go straight to question number 18. Straight wave fronts on the surface of a ripple tank approach a gap in a barrier. This is the gap in the barrier. This is the barrier. The diagram shows how the wave fronts change shape as they pass through the gap. What is happening here? This is the diffraction, okay? And yeah, this represents the diffraction of sound waves. What is the name of this effect? Diffraction, of course. A is the correct answer to number 18. We go straight to question number 19. Oh. Light travels from air into glass. What is the reflection? What is the relationship between the refractive index of glass, the angle of incidence, and the angle of refraction? Light travels from air into glass, yeah? Refractive index equals to sin angle of incidence divided by sin angle of refraction. This is one of the simplest formulas in physics, which makes option C the correct answer to question number 19. We go straight to question number 20. Which diagram shows the image correctly formed by reflection? Reflection by what? It's what? Okay, plane mirror. Good. Reflection by plane mirror. Whenever we have reflection by plane mirror, there is something particular about images formed by plane mirrors. There is lateral inversion. Images formed by plane mirrors are laterally inverted. Okay, or you say there's lateral inversion. So what does lateral inversion mean? The image can never look like the object. The image will just look like the object that is swapped. Okay, left looks like right. Okay, but what remains up remains up, what remains down will be downward. So it won't be completely inverted, it will just be laterally inverted. You get it? Yeah, that simply means that if you have a pen like this, the image in the plane mirror would be the pen that has been turned the other way around, okay, looking like this. That's what we mean by lateral inversion, okay? Yeah, so left becomes right, right becomes left. So if you have something like this, after lateral inversion, it swaps to the other side. No, that illustration is not going to be good enough. Let me use Well, if you have your left hand in front of a plane mirror, okay, if you look at the image on the mirror, it looks like your right hand. Yeah. So the hand is a perfect example of lateral inversion. Okay. If you look at your right hand, this is your right hand. If you look at it in a plane mirror, it looks like your left hand. And that is what we mean by lateral inversion. So where do you have lateral inversion? Is it here? No. Here? No. This is lateral inversion. So this is the object. The image looks like the object, but is laterally inverted. That makes option D the correct answer to question number 20. We go to question number 21. A student passes parallel rays of light through four different converging lenses. He measures the distance x and the distance y of each experiment for each experiment. Which lens has the longest focal length? Focal length is the distance between the optical center and the principal focus, okay? Yeah, that point where parallel rays pass through after refraction, and that's distance y. So we just pick the biggest value of y. That's where we have the longest focal length, the largest value of y. Y, where is the largest value of y? 3.1. Yeah. So this is the biggest focal length, irrespective of what the value of x is. So you pick 3.1, option B, correct answer to question number 21. We go to question number 22. The frequency of microwaves used in a microwave oven is 2400 megahertz. What is the wavelength of this microwave? And you know, from your knowledge of electromagnetic waves, all electromagnetic waves travel at the speed of light, which is 3 times 10 to the power 8 meters per second, or you call it 300 million meters per second. And then we have the frequency as 400 megahertz. That is 400 million hertz. How do you get the wavelength? From the wave equation, V equals to F lambda. So to get lambda, lambda equals to V over F. Okay, yeah. So the wavelength is speed divided by frequency. The speed is 300 million, and the frequency is 2400 megahertz. That's 2400 megahertz. Yeah, 2400,000,000. Yeah, so I'll fix this. So we divide it by 2400,000,000. What will this give you? All these zeros will cancel out. It becomes 3 over 24, which is 1 over 8. And 1 over 8 is 0.125 meters. That makes option A the correct answer to question number 22. 23. Which rules gives typical values for the speed of sound in a solid and in a gas? In solid, speed of sound is maximum, is highest. Why? Because the particles of solid are close together. So the particles can easily vibrate and hit each other. While in gas, the distance between the particles is large, okay, is large when compared to that of solid. That's why sound travels slowly, okay, because it takes meaningful time for the particles to move and travel to the point of colliding with each other to transmit the wave. So speed of sound in solid will be highest and in gas will be lowest. Okay, yeah, these are you have highest here, lower yes. Here, lowest for gas, lowest for gas, high for sound, for solid. That makes option D the correct answer to question number 23. We go to question number 24. A hard magnetic material can be used to make a permanent magnet. A soft magnetic material can be used to make a temporary magnet. Which rule shows whether iron and steel are hard or soft magnetic material? Um, iron, iron, iron is used to make soft magnet. Is used to make temporary magnets. So iron is a soft magnetic material. While steel is used to make permanent magnet. So it's a hard magnetic material. Let's see. Iron hard, no. Iron is soft, good. Steel is hard. That makes C the correct answer to question number 24. We go straight to question number 25. A power source is connected to a resistor XY. This is the resistor XY. In which direction are the conventional current and the flow of electrons through the resistor? No, current goes from positive terminal, flows through the wire and returns to the negative terminal. So current goes from XY. Current Conventional current goes from XY. What about electrons? Electrons are negatively charged, hence they come out from the negative terminal of the battery. and go around the circuit and return to the positive terminal. So electrons go from Y to X. Electrons go from X to Y rather. Current goes from positive terminal and travels from Y to X, go this way. While electrons go this way and go from X to Y. And this can be demonstrated with a simple simulation. We are going to demonstrate this with a simple simulation, okay? So look at this circuit, positive terminal down here, negative terminal up there. Then you have a resistor. Positive terminal down, negative terminal up there. So look at this circuit, positive terminal of the battery is down here, negative terminal is up here. We have a resistor. So let's check the current values, electrons. So this color blue here represents the electrons. Look at the direction of electrons. Electrons go upward, travel around the circuit and goes this way. So that means electrons are coming out from the negative terminal, going around the circuit and return to the positive terminal. And that's how electrons continue to travel. So this is a visual representation of what actually happens in an electric circuit. Okay. And if I click on this symbol for conventional current, this red arrow represents current. You see that the arrow for current will now be traveling in the opposite direction to the direction of electrons. Let me click on it. The red arrow, good. So you can see direction of current. Okay, so current is traveling in the opposite direction to the direction in which the electrons are traveling. So this is just a visual representation of what happens in an electric circuit. So back to the question, conventional current go from Y to X, Y to X, good. Then current goes from X to Y, correct. Which makes option C the correct answer to question number 25. We go to question number 26. Which unit is used to measure electromotive force? EMF is measured in volts. Everyone should know that. Okay, ampere is for current, joules is for work or energy, watts is for power. So question number 27. The graph shows the current voltage characteristics of a filament lamp. Which statement describes how the resistance of the lamp changes as the voltage increases? As voltage is increasing, what's happened to current? Current is increasing, right? Fine. What about resistance? As voltage is increasing, current is increasing, okay? But as voltage is increasing, current is increasing. And then the graph becomes curved such that at some point, current stops increasing and the graph begins to go along a straight path, okay? It's no longer slant. Why? Because current can no longer increase, okay? Yeah. Current has gotten to a maximum value, okay, and it starts moving along, this graph starts following a straight path. Why is it that way? Irrespective of how much the voltage continues to increase, current stops increasing. Why? Because the resistance is increasing with the voltage by a very large amount. I know the resistance is limiting the current flowing in the circuit. So if you are increasing the voltage and the increase in voltage is causing resistance to increase rather, then current cannot continue to increase because resistance is limiting the current flowing in the circuit. So it shows that the resistance decreases to zero. No, resistance decreases, resistance increases. Yeah, resistance remains constant. No, resistance is increasing. Option C is the correct answer to question number 27. We go to question number 28. In the diagram, a rod R is suspended from an insulating thread. This is the insulating thread, this is the rod R, this is Q. Okay, the rod moves away from Q. When positively charged rod Q is brought close to rod R moves away from rod Q. Rod R moves away from rod Q. Which conclusion can be made from this observation? If this is moving away, it simply means both of them must have like charges. Why? Because from the law of electrostatics, like charges repel. Okay, simply means R should have positive charge. That's the only way it can be repelled by Q. Rod R is charged, but it's not possible to identify sign of the charge, no? Rod R must be positively charged. Excellent. The rod R must be positively charged for repulsion to occur. Question number 29. The circuit diagram shows a circuit used to run a DC motor from an AC supply. So AC power supply will be here, and this will be powering a DC motor. Which graph shows the current in the motor? Now look at this. During the positive half cycle, okay, this is the positive half cycle, okay, the top here will be positive, while down here will be negative. So in what direction does current flow? Let me use color red. Current flows this way, The diode here will be forward biased, while this one will be reverse biased. No. The diode here will be forward biased, okay? You know, currents can follow this part of the red ink, and currents can also follow this part of the green ink. Because of these joints here, currents can go this way. But currents cannot flow through because this diode is in the reverse bias. See the direction the arrow is pointing, okay? The diode is in the reverse bias, so currents cannot flow along this part. Currents can only follow the part of the red ink, okay? So current then continues to go this way. No, currents cannot flow this way because this diode is also reverse bias, okay? Yeah. So current continues to go this way and flows through the motor, okay, and then returns this way, okay. Yeah. So what part does the current then follows? Does it follow this part and return to where it's coming from? Of course not, because it came from the positive terminal. So the current will just follow this straight path and returns through this other terminal, which is negative. That's what happens during the positive half cycle, okay. So the positive half cycle is marked um, correct. Okay, so current will pass through the motor. What about during the negative half cycle? Let me use color, let me use color pink to represent the negative half cycle. During the negative half cycle, this terminal down here will be positive, while the one will be negative. So current flows this way. Current cannot flow through this place because this diode is in reverse bias with respect to the negative terminal, with respect to the negative half cycle. So current can only go this way and goes through this one that is forward bias. So when current gets this way, it then passes through the diode. The current cannot go this way because this diode is in reverse biased with respect to current flowing this way. Okay, considering the direction in which this arrow is pointing. So current should only flow this way through this diode. Okay, so current cannot go back in the other direction. So the current will just come, pass through the motor and come this way and then return through this part through the negative terminal. So current comes out from the positive terminal. Let me use arrows to show the direction of current. Let me use black arrow to show the direction of current. Current comes out from the positive terminal of the battery, goes this way, goes up here, flows through this diode, continues to go this way, passes through the motor, goes this way, and the current continues its path till it returns through the negative terminal. So you can see the current will successfully flow through the circuit and pass through the motor again, and then return through the other terminal. So take note of something. During the positive half cycle, current flows through the motor in a downward direction. During the positive half cycle. During the negative half cycle, current also flow through the motor in the downward direction during the negative half cycle. Okay, so during the negative half cycle, we also have current flowing in the circuit. That simply means current will keep flowing. During the positive half cycle, current flows. During the negative half cycle, current flows. Positive half cycle again, current will flow. The next negative half cycle, current will flow. That makes D the correct answer. Because if you go by A, it simply means the system is functioning as an AC. Direction of current continuously um, um, alternating. And from the circuit, current is not alternating. Current continues to follow one path. Okay, yeah. Though the current is not actually a constant value because AC is not constant, is oscillating. But do you think that this diode acts as a rectifier? Rectifier. So they try to rectify by turning AC into DC to ensure current only flows in one direction through this motor here. So yeah, so that makes D the only correct answer to that question. Go to question number 30. Question number 30. The circuit shown can be completed by inserting components X and Y The circuit shown can be completed by inserting components X, at X and at Y. The completed circuit is a potential divider in which the potential difference across component Y increases when the temperature increases. Potential divider Potential difference across these components increases when temperature increases. Okay, well, I know that a temperature dependent resistor, which is a thermistor, okay, the thermistor is a temperature dependent resistor, and as for a thermistor, when temperature increases, then the resistance reduces. Yes. So when temperature increases, resistance reduces. Now let's come again, look at the question again. Potential divider. Potential difference across components Y increases when temperature increases. We want potential difference here to increase when temperature increases. Is it a thyristor we put here? No. If you put a thyristor here, then if temperature increases, resistance will be reducing, it won't increase. So here, this is where you put the thyristor. So here, we should have a thyristor here. Let me zoom in so I can easily draw that. We should have a temperature dependent resistor here, okay, or a thyristor. We have it here. So that when temperature increases, resistance here reduce, okay. As temperature increase, resistance there will reduce, okay. That simply means what? If resistance across X is reducing, it simply means resistance here will increase. Hence, we should put a resistor here, okay, a fixed resistance, a resistance of fixed value. So this now is a potential divider, and how the potential divider works is that if resistance here is far higher than resistance here, it simply means voltage here will be high, far higher than voltage here. And if resistance here is lower than resistance down here, it simply means voltage up here will be lower than the voltage here, okay. And if resistance here is increasing and resistance here becomes far higher than resistance down here, it simply means the voltage up here will be higher than voltage down here. Now this is a thyristor. If temperature increases, then resistance here will drop, okay. A thyristor, if temperature increases, resistance will reduce. If resistance here is reducing, it simply means resistance here will be far higher than resistance up here, and it means the voltage here will be high. Yes, okay, and the voltage here will be low. That's how the thyristor works, okay. Yeah, if temperature is increasing, it simply means resistance here is reducing. Resistance here reducing simply means its voltage will be low, and as voltage here is low, automatically voltage here will be high. Yeah, because the total voltage coming from the batteries will be shared across these two. So if the voltage here becomes low, it means this one becomes high. And if temperature is reducing, if temperature is dropping, if temperature is reducing, it simply means resistance here becomes high. And if resistance here becomes high, it means the voltage here automatically becomes higher. And it means the voltage down here will be lower. Yeah, that's what happens when temperature drops, when it becomes very cold. So if temperature drops, resistance here will be low. And if temperature increases, resistance down there will be high. You get it? Yeah. So it's a thyristor up here and a resistor down here that will accomplish this purpose. Okay. Yeah. Potential divider in which potential difference across components Y increases when temperature increases. Yeah, and it's here. If temperature increases, potential difference there will be increasing. Yeah, so that is the correct circuit combination. That is the correct circuit that accomplishes this purpose. So which component do you have on the circuit? X is a thyristor, Y is a resistor. Thermistor rather, thermistor. That's temperature dependent resistor. Okay, X is a thermistor, Y is a resistor. So D, thermistor resistor. That makes D the correct answer to the question number 30. We go to question number 31. A piece of soft iron XY has a coil of wire wound around it and there's a magnet. The end pole of a bar magnet is pulled away from the end X. When you pull the north pole away from the end X, which causes an induced current in the coil. Okay, current to be induced in the coil, fine. The magnet is now turned around. so that the north pole is on the left. Okay, we turn the magnet around so that the north pole is on the left and south pole in the right. Okay, good. It is taken to the other side. Oh, okay, now we take the magnet to the other side. So that means the magnet will be here, north pole on the left, south pole on the right. It's fine, no problem. Okay, yeah, it's taken to the other end of the soft ion and the north pole is pushed towards y. Okay, so we then push the north pole towards y. Fine. A new current is induced in the coil. Which statement is correct? Okay, initially when it was going this way, a current is induced in the coil. Now we bring it this way and we pull it towards the y end of the magnet. What happens? The new induced current is in the opposite direction and causes soft ion to attack the north pole. Well, if we are changing the position of the magnet, fine, direction of current will change to the other direction. Okay, you know, current was flowing this way initially. When we bring the magnet here, okay, the direction of current will switch. But then when we now switch the polarity of the magnet, you know, initially it was south-north. When we switched it to become north-south, direction of current will change to the opposite direction, okay? When we now move it to the other side again, then direction of current will now return to be the original direction. So by pulling it this way, okay, you know, initially we are pushing it this way. So by still pushing it this same way, direction of current will not change. Let us illustrate this with a simple simulation, okay? So let me put the voltmeter to show the deflection, okay? So in the circuit, the north pole was on the left. No, north pole was on the left. So let me switch this. Let me put the north pole on this left. Let me rotate this magnet. So I always use my FET simulation for all my illustrations, okay? Yeah. So when I pull, no, initially it was like this, right? Yeah, from the diagram, it was like this. So the first thing I would do is to pull the magnet away and take note of the deflection on the galvanometer, okay? So I connect a galvanometer. Instead of resistor, fine, there's a bulb. That doesn't make any problem. The point is that we want to check what the galvanometer will deflect. So the first thing, we pull it this way. Let me pull it to the left. I'm pulling it to the left. What's the galvanometer doing? Galvanometer deflected to the left-hand side. Did you take note of that? I will do it again, okay? This is the magnet. Watch what the galvanometer does. I'm pulling the magnet to the left. You see, galvanometer deflected to the left. Now they said I should switch the magnet. I flip the magnet and then move the magnet to the other side. I'm moving it to the other side. Now I will push the magnet towards the coil and see whether the galvanometer will deflect the same direction or the direction of deflection will be the opposite direction. Let's see. Now I'm pulling it. I'm pushing the magnet into the coil. You see, direction of deflection of galvanometer is in the same direction as what we had at first. So direction of deflection will not change since we are switching two things, flipping the magnet and moving it to the other side of the coil. Once we change two things, direction of deflection remains the same. The new induced current is in opposite direction, no. The new induced current is opposite, no. The new induced current is in the same direction and causes the soft ion to attract the end pole. Okay, now let's analyze. So is it causing the magnet to attract this pole? The polarity that will be induced here will be the one that will oppose the movement here. So here we are moving it towards the soft ion core. The polarity of magnet that will be here will be the magnetic pole that would oppose the movement of this magnet this way. And which pole is that? Is a north pole, so that there will be repulsion. You know, it is the repulsion that will oppose the movement of this magnet to the left. So it is a north pole that will be induced here. Okay, so that the north pole can be opposing or repelling this magnet, while I will be forcing the magnet to move this way. So let's see. The new induced current is in the same direction, yes, and causes the soft ion to repel the north pole. Yes, it will cause the soft ion to repel the north pole. That simply means the correct answer to number 31 is D. Yeah, this one is D. Let's go straight to question 32. The diagram shows a wire in the magnetic field between two poles of a magnet. The current in the wire repeatedly changes between a constant value in one direction and a constant value in the opposite direction. This simply means current flows downward, then current flows upward, current flows downward, current flows upward. That's what we have here. Current flows downward in line with the arrow, okay? Then it changes, flows upward. It changes again, flows downward, flows upward, downward, upward. If the direction of current is alternating, what does that mean? It simply means direction of resultant force will be alternating. Okay, yeah, from Fleming's left-hand rule, okay, if you have the field, current, and direction of motion, if current continues to alternate, then it simply means direction of motion will continue to alternate. Fleming's left-hand rule. Yeah, Fleming's left-hand rule. So if direction of current continues to alternate, then it simply means direction of motion continues to alternate. If you position your fingers and you have all of this, that's what you notice. Let me see the options we have here. Option number 1, what is the effect on the wire? The force on the wire alternates between one direction and the opposite direction. Excellent, that's the correct answer. Okay, direction of force continues to alternate since direction of current is alternating. Okay, yeah. Let's go. Question number 33. A transformer has NP turns on its primary coil and NS turns on the secondary coil. The voltage across the primary coil is Vp and voltage across the secondary coil is Vs. What is the relationship between these two quantities? Well, from transformation ratio or turns ratio, number of turns in the secondary divided by number of turns in the primary will be equal to what? Is equal to voltage across the secondary coil divided by voltage across the primary coil. So which formula, where do we have that here? Vp over Vs equals Np over Ns. Yeah, it's the same thing. You can switch this. Okay, you can switch it to become Np over Ns equals to Vp over Vs. Okay, and that can be written as Vp over Vs equals to Np over Ns. And that's what you have in option C. So the correct answer to question 33 is primary over secondary, primary over secondary is B, sorry. Correct answer to question 33 is B, okay? Yeah, voltage primary over voltage secondary equals the number of turns primary over number of turns secondary. Question 34, a magnesium ion has double positive charge and a chlorine ion has a single negative charge. Which statement is correct? Chlorine atom gains an electron to form chlorine ion. Yes, chlorine atom gains electrons to become chlorine ion. Yes. So if you want to write the chlorine atom, a molecule of chlorine gains 2 electrons to become two um, 2 moles of chlorine ions. Okay, that simply means one chlorine atom will gain an electron to become a chlorine ion. That makes option A the correct answer to question number 34. We go straight to question number 35. Which row correctly describe an example of a radioactive decay? Original nucleus, stable, emission, gamma rays, change or no change of elements. Change of elements. Gamma ray has no charge and no mass, so it cannot lead to change. So there will be no change on elements. So A is wrong. Original nucleus, unstable, yes. Emission is alpha particle. Change of elements, yes. If an element loses an alpha particle, of course there will be a change in elements because alpha particle is a helium nuclei. Okay, helium that has a charge of 2 plus. Okay, yeah, 2 protons and 2 neutrons. That simply means there will be a change. That makes B, yeah. Original nucleus is unstable. Once it emits alpha particle, there will be a change in the element. Yeah, it becomes another element once alpha particle is emitted from the nucleus. A radioactive isotope of sodium has a half-life of 15 hours. This question is technical. The table gives data from an experiment to show how the rate of decay of the isotope varies with time. The background count rate has not been subtracted from this data. What is the background radiation count rate? To get background radiation count rate, you have to start by understanding the importance of half-life in this situation. What is the half-life in this process? The half-life is 15 hours. So the time here should be 15, 30, 45, 60, on and on and on. Not 10, 20, not 0, 10, 20. That is wrong. Okay, so now we have to analyze the data we have here. How can you analyze this data? You are a physicist, you are not a data analyst. So how can you analyze this data and figure out um, what the background radiation would be? You know very well that if we have radioactivity taking place, then we know that this is what the graph of decay would look like. Okay, so this can be half-life. Okay, time taken for half the number of elements initially present to decay. So this is T, on and on and on. Once you get to 0, all of this represents background radiation. Okay, yeah. So half-life is 15 hours. Okay, the next one is the next time we have is 30 hours, followed by 45, which is not given to us, so we don't need it. It's not given to us, we don't need it. So let's focus on what we have here, 15 hours and 30 hours. Now, initially we had 400 atoms, okay? After half-life, we don't know what we have. After the second half-life, we have 115. So take note that after the first half-life, half of everything would have gone, okay? After the second half-life, which is 30, half of that half would have gone again, okay? So that means then after the first half-life, we have half the number of elements present left. After the second half-life, 1/4 would have gone again. Now let's add 1/2 plus 1/4. That gives us half plus 1/4. That will be 3/4. Okay, if you do your addition of fractions, is it 3/4? 3/4, 3/4. Yes, 3/4. So what can we do here? Now let us look at the beginning of the question again. The half-life is 15 hours, right? Good. The half-life is 15 hours. That means after the half-life, half of it would have disintegrated, right? Good. After another half-life, a quarter of it would have gone. That means total of 3/4. Now let us deal with the second half-life. Let's start from there, okay? After the second half-life, a quarter of it would have gone. That simply means after the first half-life, 2/4, okay? Half represents 2/4. That means in this case, 2/4 would have gone. Then at the second case, a quarter would have gone. Please completely ignore this 10 and 20. Let's start with 0, 15, and 30, since the half-life is 15. So after half-life, 2/4 would have disintegrated. After the second half, then a quarter would have disintegrated. So that means from here to here, 3/4 would have gone. Three quarters, okay, would have gone, okay, disintegrated. Disintegrate, disintegrated from 400 count rates, okay, to what? To this 115. So what's the difference now? 400 minus 115, what would that give us? That will give us 285. That will give us 285. So three quarters that have been disintegrated, three quarters would have gone between 400 and 115. So what we want, if three quarters represent this, what will one quarter become? Okay, if three quarters represent that 285, okay, three quarters, three quarters represents 185. Okay, let me just say this 285 represents three quarters. That simply means a quarter will be what? Will be this 285 divided by 3, and that will be 95. Good. 95. That simply means between this and this, 95 would have gone. Okay, yeah. So let me add 95 to 115. 115 plus 95, that means that's 210. Okay, that means after half-life, we'll have 210. Okay, yeah. And then yes, from here to here, we add the remaining two quarters. Sorry, a quarter. This 285 represents three quarters. So a quarter, I wrote her here. This should be a quarter. A quarter will now be 285 divided by 3, which is 95. Good. So 95, yeah, 95, 210 minus 95 gives us 115. 400 minus, okay, half or two quarters. Two quarters will now be here. So yeah, if three quarters, this is three quarters, right? A quarter is 95. Two quarters will be 95 times 2, which is 190. Yeah, yeah. Now it's balanced, okay? The difference between these two is 190, which is two quarters. And the difference between these two is 95, which is a quarter, okay? So let me erase all of this because I don't need it in my calculation. Let me erase all irrelevant details. Okay, so now the point has been made that after half-life, this is what I have left. Then after two half-life, this is what I have left. How do I get what is how do I get the initial value now? After a quarter, this is what we have. After two quarters, this is what I have. Okay, that means yeah. So during the half-life, what was the amount that disintegrated? Is 190 that disintegrated. Let me even use color green. So from 400, it lost 190. Okay, okay. So the remaining was 210. From 210, it's lost half of 190. Okay, that is a quarter. So it's lost 95. Okay, and you left with 115. Okay, it will lose half of this 95 again, which is 47.5. It will lose 47.5 again. That is if you want to put, if 60 was here. Okay, so the series continues that way. So if this was the pattern, that means if you add, half-life, this was what is lost during half-life for this to be left. That means if you add this value to what we have here, we get what was left, what was the original count rate, irrespective of yeah, if you add twice of this, yes, to what we have here, we know exactly what was left before, irrespective of the background radiation. Yeah, irrespective of background radiation. I hope this is clear, right? This was original value, okay? After 190 was lost, then we left with 210, okay? What is 2 times of 190? Because 190 is half, okay? During half-life, half of it will be lost, okay? So how do we know the exact original value? 190 times 2 gives you 380. So this is exactly, 380 is exactly what's supposed to be here, okay, without background radiation. We're supposed to have 380 here, okay? So 380, then Half of 380 becomes 190. Half of 190 becomes 95. That's supposed to be the pattern. But because of background radiation, what we were supposed to have was 380. Let me use color pink for what we're color blue for what we're supposed to have. What we're supposed to have was it's supposed to be 380. Okay, half of 380 we have 190. Half of 190 we have a 95. Okay, so that's this pattern I'm creating. 380, okay, 190, then 95, then 95 divided by 2, we will get it 47.5. But because of background radiation is now adding to it. That's why this is not 380, it's 400. So what is being added to 380 to make 400? 20. 20. Okay, so 20 was added to it. 20 was added to 380. That's why we had 400 here. 20 was added to 190. That's why we had 213. 210. After half-life, we have 210. 20 was added to 95. That's why we had 115 after double of half-life. Half-life is 15. Yeah, 15. Okay, another 15, 30. As 30, you left with 115. 20 will also be added to this 47 to get 67.5. Okay, so if 45 was here, what could have been here could have been 67.5. Okay, yeah, so we just work only with the data we have. 45 is not here, so we ignore that. Let's focus on what we have, and we've used what we have to get the count rate of 20. Please, if you don't understand this analysis, ensure you watch this part of this video again. It's very important. You must be able to analyze data like this. And if you need more help, ensure you reach out to me through my YouTube channel. This is my email address. Okay? Send a message to me, okay? Let me have your email address so I can add you to a Google Classroom and you'll be able to learn with me for free, okay? 3 days to your exam. I'll be having free classes with you. It will be a Google class anyway. It won't be a one-on-one class. And if you want one-on-one class, then you got to pay for that. Number 37, what happens in the process of nuclear fission? When you hear nuclear fusion, it is the what? It is the When you hear fusion, it is the joining together of smaller nuclei. They join together to form a heavier one. But if you hear fission, okay, if you hear fission, it is the breaking apart, okay? Like, consider this U. I'm sure you've done this topic sets in mathematics, okay? Consider this U to mean union, okay? The union of two smaller nuclei to form a heavier one. That's nuclear fusion. But when you hear fission, this I here, this U, the alphabet after the F, consider it to be the union, okay? Let it represent the union of two smaller nuclei to form a heavier one. But this I, consider it to be what is breaking it to get apart. Let this I split it and break this heavier nuclei to form two smaller nuclei. Okay, so during fission, what happens is the heavier nuclei breaks. Okay, it splits to form two smaller nuclei. Okay, good. Nucleus of an atom splits, yes. Fission, fission. Consider it to be the splitting, okay, the breaking apart, division or splitting of a heavy nuclei to form two smaller nuclei. A heavy nucleus, okay, splitting of a heavy nucleus to form two smaller nuclei. That's fission. And that's what C talks about, the nucleus of an atom splits. That is C, okay? That's fission. Why this is fusion, the combination, okay, joining together of two smaller nuclei to form a heavier nucleus, okay, or a heavy nucleus. Number 38, the time taken for the Earth to orbit the Sun is approximately 65 days. The average radius of the Earth's orbit around the Sun is 1.5 times 10 to the power 8 kilometers. What is the average orbital speed of the Earth? The speed must be given in meters per second. So we have to convert this distance to meters and convert this time to seconds. Well, that should be the responsibility of your calculator. Distance, no, take note that this is just the radius, right? That means the distance will be 2 pi r. Okay, that will be 2 times 22/7 times radius. Radius is 1.5 times 10 to the power 8 kilometer. Kilo means 1000. Okay, so what we have is 22 times 2, that will be 44 times 1.5, 100, that will be 15 times 10 to the power 9. All divided by 7. That's the distance. What about the time? Yeah, I multiply 2 times 22, I got 44, 1.5, 10 to the power 8. I remove 1 here, added it here, it became 15. Then this is 7, 7 plus 2, 2 zeros, 9, 10 to the power 9. Okay, denominator remains 7. That's the distance. What about the time? Time is 365 days. Okay, convert day to hours, you multiply by 24. Convert hours to minutes, you multiply by another 60. Multiply by 60, convert minutes to second, you multiply by another 60. Okay, so yeah, so on the long run, what we are having is that we have 44 times 15 times 15, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are dividing it by, there's a denominator of 7 here. We have to put the 7 times 365 times 24 times 3600, close bracket. 60 times 60 is 3600. So I'm going to press this on my calculator. 44 times 15, then 9 zeros. 44 times 15, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll divide it by, open a bracket, then I'll press 7 times 365 times 24, then a day. 7 times 365, 365 days, a day converts to hour, an hour converts to minutes and second directly. That's 3600 equal to 2989.8. 2989.8. 2989.8 meters per second. Expressed in two significant figures, that will be 2.99. Two significant figures, that will be 3. Yeah, that will be 3 times 10 to the power 4 meters per second. That makes option C the correct answer to question number 38. We go straight to question number 39. The sun transfers energy to the earth through electromagnetic radiation. There are two of the parts of the what are two of the parts of the electromagnetic spectrum to which most of the energy belongs? Electromagnetic spectrum, we have radio waves, we have microwaves, we have infrared, we have visible light, ultraviolet, X-rays, then we have gamma rays. 1, 2, 3, 4, 5, 6, 7. And the only two that belongs to the region that supplies energy to the earth are visible light and ultraviolet. That range, visible light and ultraviolet. Let's see. Wait, gamma and X-rays, infrared radiation, visible light, microwave, visible light, of course not. Radio waves, microwave, sorry, it's infrared and visible light. Infrared and visible light, yes. Infrared is the heat that comes from the earth to the sun, while visible light is the one we can see. Okay, this one causes excess of this can cause cancer, and God is so kind not to expose us to so much of this. Though we have ozone layer, but the ozone layer is being depleted, so ultraviolet rays is coming in, and excess of ultraviolet rays can cause cancer and other damages. So the appropriate one are infrared rays and visible light. That's option infrared and visible light. That's B, not ultraviolet rays. Sorry about that. Number 40. What does the sun produce? Sorry. How does the sun produce its energy? A fusion of hydrogen nuclei to form helium. By fission of helium, no. By the fission of hydrogen. You know, I said fission means splitting, right? Is it the splitting of helium? No. Is it the splitting of hydrogen? Of course not. By the fusion of helium? No. By the fusion of hydrogen? Yes. Two hydrogen nuclei fused together to form a helium nuclei. That brings us to the end of this, okay? There are other videos. Check the description of this video, okay? Check the description of this video. Yeah, you see other videos that are going to really help, other videos that are of significant importance. Thank you for watching this video. Ensure you subscribe to this channel, okay? And if you need to join us in the group discussion, okay, general lesson to prepare you for your exam, free lessons, send an email to me, okay? And if you want personalized tutoring, specify that you want personalized tutoring and we can communicate. Thank you for joining us. Do have a nice day. I wish you excellent grades in your exam. Goodbye.